last but not least, is Vasilis Syrgkanis, who's in Microsoft Research and who's also one of the long-term participants and an organizer for this workshop. As I was mentioning at the beginning of this workshop, min-max optimization is a classical field that has found many applications and it keeps on giving. And one of the interesting applications of it is in the in causal inference, and which of course also relates to the other program that is happening at Simon's. Nathan Kallus already introduced the connection, and Vasilis, will tell us more about it. Take it away, Vasilis.
Thanks, Costa. Yeah. So Nathan presented a paper that's very related to what I'm going to be presenting today. So I'll still give an introduction about this idea of instrumental variables and why it's important in causal inference and how then we get the adversarial formulation, and then I'll go to our main results. Because I do think that like instrumental variables is this idea that no matter how many times you see it, you always have to think a second time to understand what's happening. So to bring people at the same level, and so that you understand the remainder of the results, I'm just going to also give you an intro to instrumental variables in causal inference, and then move to the main part of sort of like the main results of the talk. Okay. So the premise is trying to do causal inference from observational data where you did not run an A/B test, but where you have a lot of unobserved confounding. So let's see one example of such a setting. Suppose that you're at a company like Microsoft and someone tells you, I want to understand what is the relationship between price and demand. So someone gave you historical data where this is the price. Typically, you use the log of the price, and this is the demand. How much of the product people bought, and these are sort of different price points that you have. And so maybe in the data we were offering some discounts. So some people got some large discounts, some people got some smaller discounts, and based on that variation of the discount that some people got and some people didn't get, maybe we want to understand what's the relationship between demand and price. And so the easy thing you can do is try to fit the data and learn that relationship. The moment you do that, you're going to learn this upward sloping curve, which says that as we increase price, demand is also going to increase. Right? And that's obviously their own claim, because then if that's our causal conclusion, then the optimal thing to do is set a price of infinity and maximize revenue. Right? The main problem is that when you deal with such observational data where the discount was not randomized but was given because of some reason, you have what is known as unobserved confounding. For instance, here, the salespeople that were giving those discounts were looking at customers, discussing with customers, trying to understand their intent to buy. And most of the times you give a discount when someone is not going to buy. So as in order to elicit, purchase, right? And then those people ended up not buying either. So, you give a discount when someone is not going to buy and they don't buy. But this is what you get afterwards, right? So you get that for people that you gave a discount and they faced a lower price, they didn't buy. And people that you didn't give a discount, they actually bought. So there is this underlying variable, which is intent to buy, that the salespeople that decided this treatment observed, but which we did not observe in the data. Right? And so, in order to understand, ideally, in order to understand the effect, we would want to add that variable into our model and fit the data with that extra variable where we don't observe it. So how can we extract causality from such data with unobserved confounding? And the unobserved confounding is a major hurdle of doing causal inference from observational data in almost every application that you can think of. Like in healthcare, if you try to understand, for instance, the effect of some drug, like immunotherapy, from non-trial data of cancer patients receiving the drug or not, typically, you're going to get some unobserved confounding scheme where, for instance, immunotherapy, more late-stage patients receive immunotherapy because it's a more recent drug than standard of care, such as chemotherapy. And so if you do not observe the stage of the disease in your data and you just look at people receiving the drug and response, you're going to conclude that immunotherapy is a terrible idea, but it's just because it's given to patients that are more late stage and so have short-term survival. So the stage of the disease is an unobserved confounder. And similarly, in the tech sector, for instance, you can get an anecdotal thing that when you try to estimate the effects of customer characteristics on engagement, you might find that people who report more bugs use the product more. And so you might end up saying, like, maybe we should increase the number of bugs so that people use the product more, but it's just that people that need the product more and more engaged already are the ones that are reporting the bugs. And so those are the people that are going to be using also the product more next year. And this, product need is something that we do not observe. So what can we do in such situations? One of the most empirically used approach, in particular in fields like empirical economics and the social sciences, is what is known as instrumental variables, where an instrument is a random variable that affects the treatment, but does not affect the outcome other than through the treatment. So, for instance, in the discount example that I presented, what could be a good instrument? One example, anecdotally, also from Microsoft, you can say, actually not from Microsoft. One example that you can use to understand the effect of a discount, if you're in a corporation that where there's a centralized approver desk where you send these discounts and they get approved or not. This to which approver you send the discount is sort of random, and so different approvers might be more or less lenient as to which discounts they approve or not, right? So you can use approver leniency, which is a variable that is going to determine the price level, is going to affect the price level, because you're going to get a smaller discount if you go to a more strict approver than when you go to a more lenient approver. So that's going to affect the discount that you get. But because this approver assignment is sort of random, this approver leniency has nothing to do with how the customer is going to purchase the product later on. And so there's no other arrow from that instrument other than through determining the price. Okay. Or in healthcare, people have used the assignment to ambulance companies as an instrument, because when you call 911 and you're assigned to some ambulance company randomly, and different ambulance companies have some biases towards particular hospitals, and so you can use that as some randomization in the assignment as to which hospital you're going to go to understand what is the quality of care at different hospitals. And that's an example that has been used in empirical work. Or an even more clear example of like more straightforward example of instrumental variable regression is what's known as A/B tests with non-compliance, or in the test sector you might call them recommendation A/B tests, where you want to run a trial but you cannot enforce the treatment, but you can do something that encourages taking the treatment, like you can encourage a person to become a member on a platform. And so you can use this encouragement as an instrument to analyze the effect of this downstream action. So let's see how that plays out in the discount example. So how would the instrumental variable regression look like? So what you're trying to do is, instead of fitting the raw data, ideally what you want to do is project the variation of the price on the instrument and then try to understand the relationship in this projected space. So say these data points over here are the data points that come from strict approvers. So they tend to be higher data points because smaller discounts were approved. Then instead of using these raw points, you're going to project to the instrument. So you're going to average those points and look at the average price and the average demand. You're going to do a similar thing for the lenient approvers. And then you're going to learn the correlation between these projected data points. And that's going to give you this downward sloping curve, which is you can interpret as the causal effect of price and demand. By doing this sort of like averaging among instrument values, sort of removing all of the effect from this unobserved confounder and only focusing on the variation in the price that's driven by the instrument. And because the instrument is sort of like exogenous variation, you're essentially regressing on this exogenous variation of the treatment. that's not controlled by the unobserved confounder. And that's why you get the sort of like the causal effect. So instruments were sort of the idea of instruments goes back to the to the 20s by Philip Wright, whose basic observation, the way that he came up with instruments was the following. So let's look at this graph. Basically, he said, because there is no unobserved confounder in the relationship between z and y, so there's no common parent that points to these two variables, and which is unobserved, we can actually estimate from the observational data what is the effect of the instrument on the outcome by simply running a regression of the outcome on the instrument. Okay. So this is this quantity over here, the outcome of a regression between the instrument and the outcome. Okay. Just the correlation divided by the variance of the instrument. So that's the effect of sort of like going from z to y. Similarly, because there's no sort of like common confounder, common parent between z and t that is unobserved, you can also estimate the effect of the instrument on the treatment by running another regression. Okay, and that's this quantity over here, delta. And then basically what he observed was, well, and this is a bit hand waving, the effect of z to y is sort of the product of the effects of z to t times the effect of t to y, which is what we want to estimate. So I've calculated the product. I've calculated one term in that product. So the other one must be the, like the ratio of the two. So the quantity that I care about is just the ratio of this first effect divided by this other effect, and you get this formula over here. Okay. And you can also formalize this idea through the use of structural equations. So a common formulation of the instrumental variable assumption is to say that suppose that we have this linear specification where the outcome is some linear function of the treatment and this unobserved confounder plus exogenous noise. And the treatment is another linear function of the instrument plus some function of the unobserved confounder plus exogenous noise. And the main instrument, the main assumption that allows you to identify the effect is that the instrument is independent of this error that goes into the first equation, which is both u and epsilon y. So the instrument is independent of these two variables. And as a normalization, let's make the mean of these two variables be 0, the overall mean. Otherwise, you need to add a constant here. Which means that if I subtract from y that treatment effect that I care about, what is going to remain is going to be independent of the instrument and is also going to be overall mean 0. So no matter what value of the instrument I condition on, this conditional expectation is going to be equal to 0.
What does it mean for you to be, are you subtracting the expectation of y, like second next to the expectation of t is 0?
Oh, so if you have the constant here, you can assume that like that's going to make a specification theta t plus a constant term plus that, and that's going to be the, but still you're going to be picking up the correct. So then from this equation, we can go to an unconditional moment restriction by multiplying this residual with z. This is still going to be equal to 0 unconditionally by a Tower law. And so we can get what the coefficient theta that we care about is, which is this ratio, which is exactly what Philip Wright concluded. And then you can also go to estimation. Instead of solving this expectation, you're going to solve the empirical counterpart of that expectation, and that's going to leave you to this estimate, which it's equivalent to what is known in empirical work as the two-stage least squares estimate. And another way to also justify this estimate is what I showed in the previous slide, which is first project the treatment on the instrument. So run a regression of the treatment on the instrument, and then run a regression of the outcome on this projected treatment, on the conditional value of the treatment conditional on the instrument. So this is another way of coming out with this formula. Okay. So there are many views of instruments, and I always find like viewing instrumental variables from different views useful because it's a very sort of like it's not a very simple, straightforward reasoning. Yeah, go ahead.
Out of curiosity, in the initial argumentation of Hilbert, there was, did he use the normalization of the mean of the unobserved confounder? I'm trying to understand if the structural equations are sufficient and necessary to get similar results.
In what sense?
With the meaning that
I think the calculating part is here, like, that the effect of this is the product of these two effects, of these two average effects. So the average effect is the product of these two average effects. Maybe you have like common factors that,
which is the independent.
These are random variables. No. There are some other random variables that affect the effect here, that change the effect, that create effect heterogeneity, and also correlate the effect here. You won't be getting that equation. But this is one way to formalize that. So what was the key assumption that allows us to identify this effect? The key assumption is this conditional moment restriction that also Nathan started with, which needs to be satisfied by our data. And this is a special case of a more general statistical problem of trying to satisfy some moment condition conditional on a set of variables, right? So M is a generic moment vector, W are some random variables, theta is a quantity you want to estimate, and Z is some subset of these random variables. And led to the development of a lot of very important work in econometrics. So the main starting point of our work was trying to do this, but with flexible causal models. So why assume that, for instance, that the demand is linear in the price, right? So why assume that the outcome is linear in the treatment, especially, for instance, when you deal with continuous treatments, right? So which is the case of a price. And so we're interested in fitting more flexible causal models, potentially also including other high-dimensional covariates that might create heterogeneity in the effect. So we're interested in such a situation where the outcome is some nonlinear, some flexible function of the treatment and the covariates plus an endogenous error. And the main restriction we're going to assume from our data is that this error is independent of the instrument and means zero, which is going to lead to a similar set of conditional moment restrictions that our model H has to satisfy. And for simplicity, let me drop the x's in the remainder of the talk. You can add them back in easily by viewing T and X as a new treatment and Z and X as a new instrument. So this is the main setup. We want to find a model H that satisfies this set of conditional moment restrictions. And this is what is known in the econometrics and causal inference and statistics literature as the non-parametric instrumental variable regression problem, finding solutions to that conditional moment equation. And it has a long history, especially post-2000. There has been a lot of progress in this problem. But and this is a nice set of work that if you're interested in the problem, you should read. But what was sort of like a bit concerning is that most of these approaches suffer the curse of dimensionality. So they use more classical econometric, non-parametric statistical techniques, which typically will incur an error that grows exponentially in the dimension of the space of treatments and instruments. And so even with a small number of variables, you're going to get a very slow convergence rate on your estimation. So that was one motivation to try to bypass this curse of dimensionality using more modern statistical and machine learning techniques. The other major hurdle in non-parametric IV is what's known as the weak instrument problem. The fact that the problem that you're trying to solve is basically what is known as a linear inverse problem. You observe, so say this is something that we observe in the data, this conditional expectation. This conditional expectation is equal to some sort of like convolution of the model that you're trying to learn. And your goal is to learn this sort of like function that is being convolved, right? So you observe the convolution of a function, and you're trying to reverse engineer and learn what was the function that was convolved. And so you can think that, like if this convolution smoothens out the function a lot, you will never be able to recover those jagged points of the original function, and that's sort of like what's implicitly the weak instrument problem. So if
example of a weak instrument.
So the weak instrument, typically this terminology is used even if your function is linear. The correlation between the instrument and the treatment is very small. Okay, so and because what you're dividing by in this in the previous slide over here in the simple thing, what you're dividing by is essentially the correlation between the instrument and the treatment. And so you're dividing by that tiny quantity. And so if that tiny quantity, for instance, is comparable to the sample size, you get like what's known as the weak instrument problem, and you get that the limits of that estimate is not going to be normal, right? Because that thing that you divide by is comparable to n or grows with n. And the point is that when you're dealing with non-parametric regression, you almost always have a weak instrument problem, because you can think of it as trying to estimate an IV regression with an infinity of treatments and an infinity of instruments, and say you're in a linear, say even in the linear case, you're trying to solve this linear moment of equations, but it's like an infinity of moment equations and an infinity of variables. And so that inverse, that's going to be the analog of the division, is always going to be an ill-posed matrix. Right? And so that the fact that this minimum eigenvalue of that matrix is comparable to n leads to the fact that non-parametric IV is always an ill-posed problem.
So for the first one, I understand that we need the dimension-free statistics. But
yes. So the second one we're not going to deal with in this talk. That was my point.
I was wondering, just for one thing, do we know the probability? I'm trying.
We don't know the probability. That's another. So the classical literature on non-parametric ill-posed inverse problems typically knows that smoothening curve.
I see. So
and the IV is a case where you don't even know that.
Okay, okay.
Yeah.
I was trying to think the old-fashioned stuff that we know from the school, like inverse Fourier and again Fourier.
So all of those are relevant if you want to understand the ill-posedness of the problem.
Right.
And you need to. This is more like a question about like functional analysis, and when you go from one function space to another, how do you preserve these
operators?
Okay. So in this paper, we are going to sort of like sidestep this problem and give a general theorem for the curse of dimensionality. But then you can combine it, and I'll maybe go into some examples with existing results for that deal with the ill-posedness to get a rate for to get like a concrete rate. Right? So we're gonna it's gonna be clear from the technical part what I mean by that. Okay. And so the way that we're going to try to address the curse of dimensionality is be able to handle this problem with arbitrary hypothesis spaces. So if someone gives me a hypothesis space over which I believe my model lies in, I want to get a rate that depends on the statistical complexity of that hypothesis space. So not just the fully non-parametric examples that is typical in non-parametric statistics, where you just assume some smoothness. Maybe you want to assume some more structured hypothesis space, but then you want to have your results decay as a function of the statistical complexity of the hypothesis space. You might also want the error rate to adapt to the complexity of the true model within that space. So if somehow there's like some norm in that space and the true model has a small norm, then you want your rate to scale with that small norm of the true model. So it's sort of like adaptive estimation. And this is where we're going to try to use machine learning techniques, which help adapt to this unknown complexity of the truth For instance, if you use techniques like lasso or random forest, you adapt to the number of relevant variables, or nearest neighbor regression might be adaptive to the low dimensionality of the covariate distribution, and so on and so forth. So the question was, can we turn this non-parametric IV estimation into a machine learning problem? And what do I mean by that? I'm gonna, look at machine learning from this narrow view of loss, loss minimization. So you're given a loss function LD, which depends on an unknown distribution of the data and a hypothesis space H, and n samples from that distribution, and your goal is to minimize that loss function, that population loss function that you don't know, only solely through access to those samples. And so your goal is this excess risk to be small for the hypothesis that your machine learning algorithm outputs. So how can we turn the non-parametric IV problem into a loss minimization problem? That was our first question. And that led to a paper we wrote with Greg Lewis a few years back, which gave an adversarial formulation of this conditional moment problem. So we can turn it into a loss minimization problem, but it's going to be an adversarial loss. And Nathan already presented it, but let me go through the derivation. So we know that these conditional moment restrictions need to be satisfied. So that means that any function f that you can choose, if you multiply this residual with that function of f, that has to be equal to 0, that expectation. And so if I produce a candidate model H, then an adversary will come and say, does there exist a moment of this form that's violated? So if I calculate the maximum violation among all test functions f, is that bigger than 0, right? And then the learner is trying to find a model that the reviewer cannot complain about. So it's trying to minimize over hypothesis this maximum moment violation. Okay, and this is implicitly, this maximum is our loss function. Pictorially, what's happening here is you have the modeler over here who is, say, presenting a candidate hypothesis. Then the reviewer says, well, let's look at the points where the approver was strict. The residuals over there, if I sum them up, they're not mean 0. Their average is not 0, so go and correct it, and then the modeler is going to slightly change to correct that violation, and this game goes back and forth until you find the solution.
Seems like a GAN.
Yeah, and so this was inspired exactly by the GAN trend back in those days. But the technical differences of the type of moments that we're testing are different. So say if you look at the Wasserstein GAN, the type of moments will look something like this, where you have a test function, you want the moment, which is that corresponds to that test function, which is pass your data through that test function and calculate this average, should match the moment if I pass these fake samples that the generator is creating. So this is a very different style of moments than the moments that I presented in the previous slide. It's actually a much more complicated set of moments, because, for instance, the hypothesis does not enter linearly in this formulation, and the test function is composed with the hypothesis that we're trying to learn. So it's a much more complicated moment problem. So there is some we're faced with a more benign game, I should say, computationally, for instance. So then the main questions was that if we do the empirical analog of that, where we solve the zero-sum game in the empirical counterpart of the zero-sum game, where we replace expectations with empirical averages, then does our estimate converge to H0 and with respect to some metric of convergence? And then how do we solve the min-max optimization problem on the samples? These are the two questions. How much time do you have?
So 15 minutes.
15 minutes. Okay, good. So I'm going to give you the main theorem and some applications of the main theorem, and if time permits, some experimental results. I should say also that this is this work is part of a rapidly growing literature in using machine learning techniques for solving the non-parametric IV problem. And what I'm focusing is on this paper that we originally formulated, this adversarial approach. And then more recently, after a few years, we managed to prove some formal statistical rates that achieve this adaptivity property that I was mentioning. Right? So most of the technical results are going to be from this paper that we published 2 years ago. So first, I mentioned like convergence with respect to some metric. So what is the metric that we're going to be measuring convergence with respect to? And this is the point where we sort of sidestep the ill-posedness of the problem. Okay. So the quality metric that we're going to use is what we'll call the projected root mean squared error, where you first take an expectation of your errors conditional on the instrument, and then take the square. Okay. And you're looking at that projected mean squared error, where you first project your errors onto the instrument space and then take the average of those squared errors. So this is a weaker than the mean squared error metric, which ideally you might want to use. So the average sort of like prediction, like the average squared error. By simple Jensen's inequality, if you can push this in and you get that, you know, the mean squared error is a larger quantity than the projected root mean squared error. So the fact that this is small doesn't really mean that the mean squared error is small. But the relationship between these two quantities is exactly what is known as the measure of ill-posedness of the problem, right? So how can you show that the projected root mean squared error is lower bounded by some fraction of the root mean squared error? This tau h, which is this fraction, is what's known as the measure of ill-posedness. And this fraction is specific to the hypothesis space that you're using and also relates to the properties of the strength of the instrument. Like, so how strong is the instrument, or does it, how smooth is that convolution? So this quantity has been analyzed for particular hypothesis spaces in the past. And even in the paper, we provide some new results on this measurable posedness for reproducing Kernel and Hilbert spaces. In the past, it has also been shown that for monotone functions in 1D, this is a constant, and also has been analyzed for the cases of growing linear functions. But in some sense, we're going to prove a result for this metric, and then you can use whatever analysis you want for bounding the measure of ill-posedness to get a result for root mean squared error. Yeah.
Sorry, for RKHS, what is the, how does it like?
For RKHS, you're going to get, you need to look at how you need to look at the eigenfunctions of the kernel, and you need to understand how the projection of those eigenfunctions onto the instrument space, how sort of like smoothened out they are. So these eigenfunctions are essentially orthogonal before you project them. Do they maintain orthogonality after you project them? And if they don't, and you know, like, especially like at what rate, this is what's going to govern the measure of ill-posedness. And this sort of like is the strength of the instrument. Does the instrument preserve sort of the orthogonality of all of this infinite set of eigenfunctions? And that's also going to hold if you have a very strong instrument, and the stronger the instrument, the more correlated it is with the treatment, the larger. And in the paper, we basically show that for RKHS, if you do an RKHS norm penalization, you're going to get a tau h that adapts to the sort of like oracle measure of ill-posedness, as if you knew that rate and you optimally clipped the eigenspace to the top, say, m eigenfunctions, and you chose them optimally based on that decay that you don't know. Okay. So that's a result in the paper, which I found interesting. And also, but you know, like you can get regimes where that decay is so fast that your rate for root mean squared error is going to be 1 over log n. N is the number of samples, so very slow. While for the projected RMSE, the rates that we're going to get are sort of always of the order of 1 over root n, or you know, whatever you would expect if you were solving a normal regression, right? Non-parametric regression. So the behavior of these two quantities can be very different. Sometimes also when this H model that you're going to learn is used in some downstream tasks, so as a nuisance model in some other estimation task, then many times this metric is sufficient to imply error rates for that downstream parameter that you care about. So sometimes you don't even need to argue about this and use our metric, our guarantee directly. So that's an important slide. And then given that, this is our main theorem. So first, let me say it in English, and then because the actual definition of the theorem is quite involved, and then I'm going to unwrap it step by step. So if the set of test functions that you're testing is rich enough, and importantly, if you change your objective to add what we will call stabilizers to the test function, and on top of stabilizers, also regularizers of the complexity of the hypothesis in the function space, which inject strong convexity to your overall loss, while maintaining identification of the causal model, we can achieve fast estimation rates that adapt to the statistical complexity of the hypothesis space H and the complexity of the true model H not within H. Ask it after, because this is very vague. Every one of these things is like, you can interpret it in a gazillion ways. So but if you want to take a message, this is the message. If you want to learn what it is, let me go through that. So, sorry for that one. So if F, what does it mean reaching out? So we need that the test function space contains functions that look like this. So you take two hypotheses in your original hypothesis space. Okay, you take their difference and project them through your instrument. So this conditional expectation needs to lie in the in the function space. Okay, so that's one condition. You can also allow for approximation errors, and there's going to be like some extra bias things if this is not contained but is close. But this is the main theorem statement. And then what was the other thing? To add stabilizers. So instead of just solving this minimax problem, we're going to add a penalty over here, which penalizes the second moment of the test functions. So if you recall, also Nathan had some sort of like stability addition to his minimax loss, but was qualitatively very different. It wasn't just the second moment of the test functions; it was the second moment multiplied by the residuals, so which has a different behavior, right? So here we don't even add residuals in this second moment. It's just the second moment of the test function, and the reasoning why we add this is also very different to the reasoning why sort of Nathan added it in order to get the efficient GMM. Here we're going to add it to get these fast estimation rates. Okay? So you add this thing. This is very different from the classical regularization approaches in machine learning. So this is not a regularizer because we're not multiplying it by some quantity that goes to 0. This is really 1 over here. So it really changes the loss function even asymptotically, and it changes it in a way that makes the sort of like the loss function be much more stable. The point being that without this thing, if the H was so what the test function is trying to do is essentially match the sign of this error term over here, right? And so even if your H was very close to the truth, and so H minus H naught was very good, was very small, the test function is gonna be sort of like alternating by trying to match the sign of that error, even if that error is tiny, and that you can create instabilities in your loss function, which can lead to slow rates of convergence. Well, when you add this square term here, you can complete the square and essentially argue that what the test function is trying to do is learn the conditional expectation of this conditional on Z. So the test function is trying actually to solve a regression problem that tries to learn what is the average bias conditional on Z. And so if that bias is small, then this test function is going to be small. So that's the intuition behind the stabilizers. Then of course we're going to add regularizers, which are sort of like for the standard reasoning that we want to penalize functions with large statistical complexity within the function spaces that we look at. So this is penalizing the statistical complexity of the F function, and this penalizes the statistical complexity of the H function. And the norm here is going to be dependent on whatever hypothesis space you're using. then observe that by adding this extra penalty, we don't change what is the model that's being identified, because in the limit, H is the correct thing and F is 0, that's the equilibrium, and whether we added an F squared doesn't change. So, you know, the same model is going to be the solution to this, and with or without the penalty. The regularizers are going to 0, so that doesn't affect the limit thing that we converge to. Right? Then, if you do that, what you're going to get is a rate that looks like this, where the leading term depends on what's known as the critical radius of these function classes that we use. So the function class of the test function class, and a function class that's related to the H. In fact, you can actually decompose it to statistical complexities of the H function and the F function, but this is an even tighter analysis. Just need to understand the critical radius of this function class. And the critical radius is really what I mean by fast rates. So the critical radius is a notion of statistical complexity that's been introduced in the last like 10, 20 years in statistical learning theory to be able to argue tight fast rates in regression problems, in non-parametric regression problems. And so here we essentially are able to extend that technology to minimax problems. So not just square loss problems, for instance, which is the classical case where the critical radius has been used. And if like without this, for example, this stabilization argument, we were only able to get rates that look like the root of that critical radius, which are sort of like the analog of slow rates. So think of it for the case of parametric classes, the critical radius is 1/√10. So without the stabilization, you would be getting results of the order of 1/n to the 1/4, which are not tight for parametric classes, right? So when you have a parametric class, you expect 1/√10 rates. And this is what allows us to complete the analysis and do that. And so that's the, like the main statistical result in this paper, being able to get that rate. And the other main statistical result is that the leading term is scaled by the unknown norm of the true model. And this is enabled by the use of the regularizers. So the regularizers allow you to be adaptive to this unknown complexity. But this is a more standard trick. Even for square losses, by adding regularizers, you can get such adaptivity results. Being able to get a critical radius was more non-standard. So that's the main theorem. 5 minutes or no minutes? Yeah. So let me give some example function classes and also talk a bit about the optimization. So how do we solve the optimization problem? Well, generically, you can do subgradient descent. Like you say your hypothesis space was parameterized by some parameters, you take a gradient step, and in here you take a gradient of the value of your function evaluated at the optimal test function for the current estimate of the thetas. And the question is, how do you solve that? And this is one approach that you can use in the following concrete setting. Suppose that the function space that you care about are functions that are solely defined via shape constraints. So we assume that the treatment is scalar, the instrument is scalar, the outcome is scalar, and we're trying to learn like a single dimensional function from 1D to 1D, and we're only imposing shape restrictions on that function. So for instance, you might want to learn a demand function from a price to a demand, and you want to impose that the demand is monotone, which is natural. Then we know how to bound the critical radius of those functions. So that gives you the critical radius part. And then you can also solve the optimization problem by parameterizing the function by the values that it takes on the samples that you got. And then the interesting thing is that the inner optimization oracle that if you apply subgradient descent, is equivalent to an isotonic regression, and for which we have computationally efficient methods for solving it. Okay. So you can solve this minimax problem for the case of shape constraints using some a gradient descent versus an isotonic regression oracle, right? And that is also efficient, and so you get a fully efficient, computationally efficient algorithm for solving this. And also prior work, and you can also add other constraints like ellipsis or smoothness, And prior work had also bounded the measure of ill-posedness by a constant. So for this class of functions, you get a complete theorem even for mean squared error.
I understand that the isotonic is to bypass the existence of the expected value. The problem is convex concave or not necessarily?
Yes, in this parameterization. In this case, the parameters are what is the value of the function on the samples. So you have n parameters.
Okay.
So in that n parameters, it's a convex concave, right? And it's not even like, and also you can you can solve this.
Yeah, I got with the trick.
For RKHSs, you can get a closed form solution using the kernel trick, and we also know what the critical radius is for many reproducing kernel Hilbert spaces, and we have an analysis in the paper for the measure of ill-posedness, so there you can also get a complete theorem. And then goes to more like heuristic approaches. You can use this with neural networks, where we sort of know what the critical radius is, but we don't know how to solve the min-max optimization, and that's sort of like one of the things we're trying to do here. And another nice thing that I have for optimization is that we can also solve this optimization problem with access to a regression oracle and a classification oracle. So the main point is that this L2 penalty that we added on the test function actually makes the loss of the test function player in the output space be strongly convex. And so a very simple algorithm like follow the leader, because of the strong convexity, is a no regret algorithm. Okay. And then if you write down follow the leader, it basically becomes another sort of like regression problem where you're trying to match these labels and to solve the square loss. So that's one, you need a regression oracle over the test function space. And then you just best respond with the modeler at every period. And that is a classification oracle. It's like a weighted classification oracle that tries to match the labels of the test function. And with this, by running a no-regret dynamics of best response versus FTL, you can get an ensemble of hypothesis H, which solves the min-max problem. And this is how we get random forests. So you can sort of like best respond with a decision tree, and the other person, the test function space solves like a regression with a random forest, and then you ensemble and you get a regression, you get a random forest that solves the min-max problem. Okay. Again, there are several, going from this theorem to actual random forest, there are several open questions that I find very interesting, both on the computational side and on the statistical side. But this motivates one algorithm that we use that performed very well in experiments. And so I want to leave you with that. There's some very interesting open questions with analyzing random forests for this non-parametric IV, and it's actually one of the best performing algorithms in experiments. And with that, I'd like to close. Thank you very much.
Thank you. Thank you for the great talk. Any questions for Vasilis?
Very nice talk. Thank you very much. Out of curiosity, the FTL, if you can go a little bit to the equation, I was trying, like very intuitively, if it was a mean and I didn't have the F of Z i's, I would say that it is like a square mean loss. But now with the max, how we should interpret it?
So it's like there's no max here. Right? This is like what the FTL is solving at every step. So think of the min-max game, right? The min-max game, right? You want that's not here. Okay. Anyway, the value of the game, you look at the value of the game that's inside the min and the max, right?
The max is over the F.
The max is over the F, right? So,
okay.
One player is trying to maximize that value over F, and that's if you can complete the squares and you can get the square loss.
Fine.
And so FTL is exactly that, and you get strong convexity in the empirical norm, L2 norm, and so it becomes, like a. You can prove that you get rates, assuming that the function space is convex. That's an assumption, meaning convex combinations of the functions are in the function space. So that's one assumption.
And do you have about the ill-posedness for that case? Is there?
So here, no. This is just for solving the optimization problem. the random forest and ilposeness, that's a different beast. I don't think you can, like these are discontinuous things, and so you won't even get any measure. It's only if you think about them as approximators of smooth functions that maybe you get some ilposeness. So I think you really need to go to forests. You just have like a decision tree with a discontinuity. Like
I see.
Right, but yeah.
So as a last question for me, the ilposeness affect also the consistency of the result at the end of the day? Yes.
If you care, so if you care about consistency with respect to the mean squared error metric, yes. But
the
if projected,
you change
it's sort of like a semi-metric. Like it might be right. So
okay,
you always get consistency with respect to the projected metric. But here for random forest, even that is a bit like getting like tight rates, even for the projected metric, is interesting. The rates that we're getting here sort of like sort of slow rates. You get like the 1/4 of the VC dimension or something of 3.
Thank you very much.
Yeah.
So yeah, thank you for the talk. I guess my question is around the relative complexity of the mappings from Z to X on one hand and from X to Y on the other hand. So what I'm wondering is, let's say you might have a very non-smooth mapping because it's fully non-parametric from Z to X and a very smooth mapping from X to Y. That seems to mean something about the classes of functions you use for H relative to F, say, or vice versa. You could have a very non-smooth mapping from X to Y, but a very smooth mapping from Z to X. I'm wondering like how or where that appears in your analysis.
So I think the only place where it appears is the test functions are projected through the Z, right? So the test function space needs to be H of X conditional on Z.
Right.
So if that smoothens a lot the function space, then you get a sort of like a much smooth set of test functions. Even though your original H might have lived in a more complex set of test functions. Is that what you meant?
I think so. I mean, somehow like it's a property of your original data that like H2, X to Y is like a very messy function, but maybe Z to X is a very smooth function. So I'm just wondering.
So if Z to X is a very smooth function, you might get like ilposeness. That will affect the ilposeness, I believe.
I see.
Right. So if Z to X, for instance, is a Gaussian, a centered Gaussian around the Z, that is a very smooth function, and that will give you tau H will actually blow up. So that will enter there. Yeah. So I think the relation between Z to X enters primarily in the measure of ilposeness quantity.
Thank you.
All right. If there are no further questions, let's thank Vasilis again and all the speakers of this conference.
Thank you.